All right, then I want to welcome you all to the first paper session. We're going to have this session on game solvers, and we're going to have 3 talks. So that means for the next 1 hour, we're going to hear interesting new research on this topic. And the first talk, and I want to invite you to share your screen, is on relevance zone reduction in game solving. Go ahead.
Okay, can you see my screen?
Yes.
Okay. So then I will start.
Sure. Yes, go ahead.
Okay. Hello everyone. My name is Chi-Huang from National Yangming Jiaotong University in Taiwan. Today, I'm happy to present our paper entitled Relevance-Zone Reduction in Game Solving. First, let me quickly introduce game solving. The goal of game solving is to find the game theoretic value, which is the outcome of the game, assuming each player plays perfectly. For example, in this tic-tac-toe case, we can build an NO tree to figure out the best strategy for both players, and that gives us the game theoretic value, which is X win. Now let's look at an important technique in game solving called Relevance-Zone. Relevance-Zone is a powerful pruning technique that can greatly reduce the size of the solution tree. This technique has been widely used in game solving, and we will refer to it as R-zone from now on. Basically, an R-zone is the area on the board that both players should focus on. Since moves inside this region are most critical to deciding the outcome of the game. And R-zone can be generated automatically during the search. For example, here's a 7x7 kill goal solution tree. Depending on white's current strategy, 3 branches are generated. In the end, the area where white stones live safely is marked in green. That's the R zone. And it automatically merges and propagates upward to the soft nodes in the tree. And different strategies can produce different R zone. If white plays at this position instead, the R zone would like this. If white play at this position, the R zone can become even smaller. Okay, next, let's talk about how R zone enables pruning. Once the R zone of a position is determined, any changes outside the R zone won't affect the result. White can still win using the same strategy. So if 2 positions share the same board configuration within the R zone, the same strategy can be reused. The R zone pattern table is a technique that implements this idea. For example, in this position, we first remove all stones outside the R zone, then store the remaining pattern in the R zone pattern table. Later, if we encounter a new position like these 2, we check if its pattern inside the R zone matches the pattern we have already stored. Since these 2 are identical inside the R zone, we don't need to solve it again. We can just reuse the null outcome and safely print these entire branches of the search. If the R zone is smaller, it can match more positions, And in this example, the smallest R zone allows more matches and make the search more efficient. This brings us to the main contribution of our work. Since smaller R zones are more valuable, we aim to find even smaller ones. However, with only a single solving attempt, it's hard to tell whether an R zone can be further reduced. To address this, we propose an iterative R zone reduction method, or RZR for short. It repeatedly resolves the same position, gradually guiding the solver to produce a smaller R zone. So first, we let the solver solve the position directly. The R zone generated at this stage becomes our target for reduction, and it is considered the baseline. Next, based on the generated R zone, we mark an area on the board and require the solver not to let the R zone overlap with this area during solving. This area is called constraint. We add points outside the R zone to the constraint and also pick one point inside the R zone to include. This ensures that the R zone won't expand while shrinking by at least 1 point. You can see that this R zone is now smaller than the previous one by exactly 1 point. Then we repeat the same process again. At point outside the R zone, pick 1 point inside and solve it again. But sometimes it may fail. This happens because the point we picked might actually be needed by the R zone. So the solver may not succeed in some case. If a failure occurs, the constraint is then chosen based on the last R zone that was successfully solved. And this algorithm stops if it fails to solve the position k times in a row. As mentioned earlier, we first lock all points outside the R zone to prevent it from expanding. Then we bend 1 point inside the R zone to shrink it further. And we propose three different strategies for selecting the constraint point inside: random, erosion, and heat map. So the first strategy is the simplest, random. As the name suggests we just randomly pick 1 point within the current R zone to bend. This can sometimes get lucky and remove a key point quickly, but more often it will fail. Next is erosion. We assume that points already occupied by stone are harder to shrink, so we only select empty point inside R zone. Since the R zone usually shrinks inward from the boundary, we count how many neighboring points lie outside the R zone and start reducing from the ones with the highest count. For example, in this case, there are 2 points with 2 neighbors lie outside the R zone. meaning they have the same priority. So we randomly pick one of them as the constraint. Next is heat map. We combine all R zones from the entire solution tree. So each number on the board represents how many R zones cover that point. Then we select the point with the smallest number as constraint. The advantage of this approach is that it minimizes the number of invaded R zones. For example, choosing this point only invaded 8 R zones, which gives us a higher chance to solve it. And we also modify the R zone pattern table and store the previous solved R zones into the table. And for the later iterations, it can be reused. In our experience, we randomly select 10,000 R zones from the solution trees for previous solved 7x7 Kyogo openings as our baseline. And we set the algorithm to stop if it fails to solve the position 5 times in a row. We analyzed the performance of the 3-point selection strategy. Heat map achieved the best result, reducing the R zone to about 86% of its original size, while random performed the worst, but still reached around 92%. We also analyzed the impact of enabling the R zone pattern table. Reusing previously solved R zones reduced the average number of nodes by 29% and brought an extra 1 to 2% R zone reduction. Finally, across the 4 openings, using heat map together with the R zone pattern table achieved the best overall performance. We also analyzed different stopping conditions. As you can see, even if we stop the algorithm immediately after the first failed resolve, the R zone can still be reduced to about 90% of its original size. We set the final stopping condition to 5 because increasing it by just 1 requires about 12% more GPU computation, while the R zone only shrinks by around 0.2%, making the reduction efficiency too low. And here's an example of the position with the largest R zone reduction rate. As you can see, without using our RZR method, the R zone covers the entire board. After applying RZR, the R zone becomes concentrated in the lower left corner and shrinks significantly. The reason of this difference is that in this position, white's territory is initially divided into 3 regions: upper left, lower left, and right half. In the 4 key points, 4 key positions shown here, the baseline is not restricted by any constraint. So white's living area are scattered across the board, causing the final R zone cover the entire board. However, after applying the constraint, all R zones become concentrated in the lower left corner, causing the R zone of the root node shrink accordingly. In conclusion, we proposed an iterative R zone reduction method that guides solvers toward smaller R zones. And we also introduced 3 constraint generation strategies and an enhanced R zone pattern table to make the search more efficient. Experiments show that we successfully reduced the selected 10,000 R zones to about 86% of their original size. These reduced R zones can be stored and reused permanently, paving the way for solving larger boards or games with different rule settings. So that's all for our work on R zone reduction. Thanks for your attention.
Thank you very much for this wonderful talk. Are there any questions by the audience? So you can use the Q&A. You can raise your hands if you want to ask any questions. So maybe let me start for now with a question. So the methods you proposed, do you see how they can be adapted for other games, or to frame the question differently, what are the conditions that you need in a game to be able to use these techniques?
Okay, so if R zone can apply on the game, then the game can use our method. So then we can apply our method on the game.
Right. So all the games that have the right properties for the R zones.
Yeah.
Then you can just plug in your methods. Nice.
Yeah.
Okay. So did you already try larger boards?
No. Actually, that's our future work.
Sure. Are there any further questions from the audience? Again, maybe just as a general note, also feel free to just fill in the Q&As, maybe already during the talk, and we can access the questions then later on. So there's a question from Lucas. So the question is, what are some typical runtimes for instances in the experiments?
Sorry, can you say again?
Yeah, okay. So what are some typical runtimes for instances in the experiments? So what are typical runtimes basically for what you did?
Typical runtime. I it's about 2 times longer than the first. It take so iterative resolving
Yeah.
The time the iterative resolving take is almost same as the first iteration. As iteration 0, the initial so So the resolve time is basically same as the first round that we first solve this position. Yeah.
Okay. So maybe also a general note on the Q&As. What we can do is we can mark these questions as answered live. And I think if you access these questions, you can also make some comments on these questions. So, Lucas, if you want to have a follow-up, you can feel free to do so. And Chi-Huang, you can also answer these follow-ups in the Q&A. So for the sake of time, I want to thank you again for this nice talk.
Okay.
And we are going to move on to the second talk of this session. So Taylor, if you could share your screen.
Sure.
All right. So interestingly, this group where Taylor is a part of has two very interesting papers placed in ACG. And the first one we are going to see now is on a linear Clobber solver. Go ahead, the stage is yours.
Sorry, I need a timer. Okay, I have a timer. Okay, hi everyone, I'm Taylor. I'm from the University of Alberta, and today I'm here to talk about SEGClobber, which is our group's linear Clobber solver. So firstly, Clobber was invented in 2001 by Albert and others. It has black and white stones and empty spaces, and on a player's turn, their only legal moves are to move one of their own stones to replace an adjacent opponent stone. So for example, black can move this second stone to the right. Likewise, white can move this third stone to the left. Note that you cannot move to an empty space, so white cannot move this last stone left. An interesting property of this game is that it breaks into independent subgames very frequently. Anytime there's an empty space on the board, it produces independent regions of the board. So this board is equal to a sum of this board here. Firstly, some notation. This superscript denotes repetition. So this black-white to the 3 is just black-white, black-white, black-white. Albert and others made two conjectures about linear Clobber. The first is that black-white to the n is a first player win for all n not 3. They verified this up to n equals 19, and we push this number to 50. Their other conjecture is that black, black, white to the n is equal to this multiple of the game up. This is the floor of n plus 1 over 2. And they verified it up to 17, and we pushed that to 28. Additionally, Chen and others recently proposed a proof for the first conjecture. Now I'll talk a bit about some of our methods and the components of the solver. We have a transposition table that's based on 64-bit Zobrist hashes, and there's four-way set associativity. So given the index bits of a hash, you'll find 4 table entries for any given value, and there's a replacement policy if the set is full. The contents of a table entry include the win or loss value of a position. Occasionally, there's a heuristic value and a best move according to the heuristic in place of this. We use an iterative deepening approach that I won't talk much about. The basic idea is to do depth-limited searches up to a maximum depth and iteratively do more searches from the root node, increasing the maximum depth each time. And at the max depth, we evaluate the positions with the heuristic function instead of searching further. And we use that information to guide the move ordering. Additionally, there's an age and a depth, which are used by the replacement policy. So think like most recently used or least recently used. We have an endgame database, which represents all games up to and including length 16. So this includes both single subgames and sums of games. This is 3 to the 16 or 43 million games. In practice, we only need to store 866,000 entries, which is about 2% of this number here. More on this later. The contents of a database entry include the outcome class, which denotes how a game relates to 0. This character here means not comparable to. So some games are not comparable to 0. Additionally, we store bounds along these two scales. First one is multiples of up, and this is multiples of up plus a star. Occasionally, during search, if the outcome classes or the bounds are known for all of the subgames, then the value of the result of the position can be determined without further search. For example, if all subgames are positive, then black wins. Additionally, we store the non-dominated moves for each player. Some moves are provably worse than other moves, using this concept of greater than or less than, and so we don't play those bad moves during search. Additionally, if two moves have equal value, we only keep the simplest of the two. And this is defined in terms of a complexity score, which is also in the entry. The complexity score is an estimate of how difficult a game is to solve, based on some properties of its game tree. More on this later as well. We also store a simplest non-dominated move and a link to a simplest equal game. During search, sums of games are sometimes replaced by other equal but simpler sums. And lastly, we store the board itself so that it can be recovered from the entry. We impose a normal form on Clobber boards. We'll use this board here in this running example. This has two benefits. By normal form, I mean that we want to convert this into a unique representation. The two benefits of this are that the transposition table hit rate will go up, and we can make the database smaller. So we define the shape as the sequence of subgame lengths. Here we have 3, 4, 3, 1, 2. And there are 5 steps to reach the normal form. First, we remove these subgames with length 1. Second, we omit these redundant empty spaces. Third, we sort the subgames so that the shape is in decreasing order. So now the shape is 4, 3, 3, 2. And at this point, we've reached the relaxed normal form. The database stores only relaxed normal form games, which is where that size reduction comes from, the 2% figure from earlier. There are still 2 more steps to reach the full normal form, and they treat these subgames like binary numbers, where the black stones are the digit 0 and the white stones are the digit 1. So we flip some of the subgames if it would make them greater. So this last subgame gets flipped to 1, 0. And additionally, this first subgame gets flipped. And then lastly, we sort the equal length subgames, again using this binary representation. So these middle 2 subgames have traded places. Now talk a bit about the complexity score, just giving the general intuition and not the equation. So here is a game, and these nodes here are options or moves within the game. And this is the CS3 or complexity score 3 of the root node. And it's equal to 2. What we're doing is we're counting the non-strictly dominated moves, which are these black nodes, and we're not counting the strictly dominated ones. I say strictly dominated because it could be the case because, I say non-strictly dominated because it could be the case that these 2 black nodes here are equal in value. So we also define a recursive extension of this, which we follow the non-strictly dominated moves and recursively count them down the tree. And the value of this is 4. During search, a game G1 can replace G2 if G1 is simpler according to this score. And additionally, G1 has to come before G2 in the database. This essentially means that G1 cannot be longer in terms of the stones and spaces. This is to prevent cycles where you do a substitution, you play some moves, and then you do another substitution and end up back where you started, causing search to never terminate. Additionally, the database stores the simplest such game, if one exists. Not all games in the database have simpler games. The first thing that our search function does is simplify the current position. We'll use this as a running example. This wraps around the screen. The first step is that we set aside the large subgames that cannot be in the database because they're too large. That includes this entire top row. We'll be ignoring this row for most of this example. Second, we delete single p positions using database lookups. This game here is a p position. Now we sort these subgames in order of decreasing length. Now we're going to start to replace games with their simplest equal games. To avoid enumerating all combinations of 3 or more games, we instead use a sliding window that we just slide over the board. And here the sliding window matches these 3 subgames. So we replace these games here with this game over here on its right. That game is here. And now we enumerate all of the pairs, and we do those replacements. And then lastly, we replace the single subgames. And here are the reductions in the complexity scores from the left game to the right game that takes its place. Next, we reconsider those previously ignored games, which is this top row, and we delete subgames that don't have any moves or which are visually inverses of each other. This game has no moves, and these two are inverses, so we delete them. And lastly, we convert to normal form. Our search algorithm is a minimax search algorithm. The first step is to simplify the board, as in the previous slides. Then we check the database and then the transposition table to see if the position is already solved. We try to put off playing moves for a while. Third, we try to solve the position using the outcome classes and bounds of the subgames. Fourth, you'll have to check the paper for more details on this or ask about it after. So for certain subgames GI with known outcome classes, we try to remove it and solve the smaller board and use that result to solve the larger board. And then lastly, we have to play moves. The move ordering is informed by several features, such as the outcome classes of games, the database's simplest moves, the heuristics best moves, and playing in the middle of subgames to break them down faster. Now look at some ablations. Here we look at random boards with 58 contiguous stones and no empty spaces. Every vertical section of this graph represents the same game. And we're comparing the full solver, this blue setting, to the orange one, which is removing one feature. So here we're looking at no substitution. This is the most important part of our solver, the substitution. And then now we consider boards of length 60 to 66, just sort of randomly. This is comparing the solver to the non-recursive complexity score. So it will give worse substitutions. And this is also a pretty big difference. Pruning dominated moves is also a big performance increase in some cases. And the iterative deepening is only occasionally useful. It's likely that our heuristic function isn't general enough. Now we'll look at some of the conjectures. The black-white conjecture. Here are the number of pairs on the x-axis, and the y-axis is the base 10 logarithm of the solve time. This first dot here is notably higher than the next ones because this is also counting the startup cost of the program. We don't clear the transposition table between runs, and we run these sequentially from 1 through 50. We use this many table entries, transposition table entries, and we play a hard-coded move at the root node. Each next case takes about 1.6 times as long to solve as the previous one. We only solve for black due to symmetry. We don't need to show that white can win playing first. Here's the previous record of 19, and on a clean start with no prior transposition table, we can solve it in 0.08 seconds. The new record of 50 is here, and it wraps around the screen here at the end, and takes about 35 hours. Note that this time here is not cumulative, and this includes the transposition table from running all these prior cases, 1 through 49. The second conjecture, the black-black-white, is a very similar setup. Here are the number of black-black-white groups on the x-axis. We use the same number of table entries and don't clear it. We don't play a hard-coded move this time. And each next case is about 2.12 times as long to solve. And we have to solve for both black and white. Here's the previous record. Here's the time on a clean start with no table. And this is 28. It took about 9 hours. Here's a download. The source code is available under an MIT license. And that's it.
Yes, thank you very much for this nice talk. Again, if there are questions from the audience, feel free to use the Q&A or raise your hand. So I think it's awesome that you provide this this via GitHub. I also just checked, so your input is just stating a black or white, right? So you just have this string that represents this the position you're interested in, right?
Yeah, the position is the board and then the first player.
Oh, I see. Okay, perfect. And when you showed this new record, which took like these 35 hours or so, right? And on, yeah, right. And you said that this time is not cumulative, right?
Yes.
So can you elaborate on that? So I guess having like 51 is not just the factor of 1.6. Is that correct?
So the way we timed it is we just ran these sequentially 0 through 50, and we didn't clear the transposition table, and each time starts when the previous case is done solving. Does that answer it?
Yeah, I see. And then the 1.6 is this factor for just one, yeah, how to say that? Yeah. Let's say the additional time. Yeah, I don't.
So, sorry.
Go ahead.
So what we did is we looked at this like reasonably straight section, and we used the slope to estimate what the next step would be.
Yeah, right. Okay, so there's a question in the Q&A, which states, you did use Zobrist hashing, right? How did you choose your Zobrist hash seeds? Are there well-known numbers for Clobber, or did you benchmark their performance?
To be honest, we didn't really put much thought into that, though we did verify the correctness of the solver against some other tools. So we're reasonably confident that the results are correct. But as for performance, I'm not sure. Future work.
Yeah, okay, perfect. Thank you. All right, are there any other questions from the audience? A quick one. We might still have time. And if this is not the case, I want to thank you again for this wonderful first talk. And I would say, since I don't see any further questions, you can feel free to share the slides of the second talk, which will be on a Minimax-based combinatorial game solver. Yes, the stage is yours again.
Okay. Hi, everyone. I'm Taylor. I'm from the University of Alberta, and today I'm here to talk about MCGS, a Minimax-based combinatorial game solver. MCGS is a framework for solving sums of short two-player games. Short games are those which are both finite and loop-free. Given a sum of games and a first player, we want to efficiently find the winner. This is assuming the normal play convention where the last player to move is the winner. There are some existing combinatorial games tools, such as CG Suite. CG Suite has many features, however, it's based on canonical forms, which makes it very slow. To illustrate this, we consider the empty 1x16 no-go board. CG Suite finds its canonical form in about 8 minutes, whereas MCGS finds the outcome class in about 1.6 seconds. This is without search enhancements, such as a transposition table or a database, so just a very bare-bones minimax search. To further illustrate this point about canonical forms, here are some Clobber boards and their canonical forms. As we add more stones, these tend to grow, and at 9 and 10 pairs, they get really large. So canonical forms are not efficient for solving win-loss questions. That's where MCGS comes in. Our goal is to create an efficient and general framework for solving games. We want to apply some lessons that we've learned from previous solvers, such as those for variants of no-go and clobber. A user can simply implement the rules for a new game and then benefit from MCGS's search engine. This is much faster and easier than writing a specialized game solver from scratch. The source code is C++, so it has less overhead than some scripting languages, like, say, Python or CG Suite's scripting language. We have support for both partisan and impartial games, using different search algorithms for both. Partisan games use a Boolean minimax approach to find the winner, whereas impartial games use the more specialized algorithms to find the nim value. A wrapper can create impartial versions of any implemented game. MCGS comes with a testing framework. Inside of input files, you can specify positions to solve as sums of subgames with first players and expected results. Running these files gives you CSV or HTML output with the search results and various statistics about solve time and node counts, etc. We include thousands of test cases, many of which we verified with other tools, such as CG Suite or other solvers. It has extensive documentation with varying levels of detail. So for general users who are not programmers but just want to solve games, there is a how-to for that. And for developers, we have instructions for adding new games, as well as comprehensive documentation about the system and its many implementation details. Many games are supported, such as these basic combinatorial games, the rationals, nimbers, switches, ups, and stars. We also have support for one-dimensional strip games. So these blue games with the stars are coming in future versions. They're also two-dimensional grid games, and the system is not limited to these classes of games. We also have Kales. Now I'll talk a bit about some of the techniques we use and components of the system. We use 64-bit Zobrist hashes. And this is used to index both into the transposition table and the endgame database. We use a two-part hashing scheme. Each subgame has a local hash, lowercase h, and then each sum of games has a global hash, capital H, which is computed from the local hashes, as we'll see later. As with any Zobrist hashing solution, we have a Zobrist table Z. It has random integers and is indexed by a location color pair. So for example, here is the local hash of this Clobber position. This is the exclusive OR operator, and we're taking the XOR of the Zobrist table lookup at each location and color pair on the board. So here at index 1 is the white stone, corresponding to this. And lastly, there's a special code for the game type, which is Clobber. An important note is that a specialized solver might only have a few colors indexable in the table, like black, white, and empty. But MCGS's table allows arbitrary integers that are 128 bits or less. This will come up on the next slide. We want to compute the global hash for a sum S and a player P. This is done in a few steps. First, we sort the subgames. These subscripts here on these games are obtained after the sorting. And this is because sums that differ in the order should still produce the same hash. So G0 plus G1 should give the same result as G1 plus G0. Next, we compute the list of the local hashes, which is here. On the right side here is an abbreviation. And then this is the definition of the global hash. So this Zobrist table lookup has a subscript of sum. We have different Zobrist tables for different purposes. In this case, we're transforming these local hashes so that the result of XORing them doesn't cancel out some of their contents. This two-level recoding scheme prevents the contents of them from canceling out. And this yields different hashes, even if we have sums of several thousands of copies of one game. There's an abstract base type for games, and games have several functions that they must implement. Among these are play and undo move, a function to compute the local hash, printing the textual representation of the game, and creating a move generator. A move generator just produces all of the moves for a given subgame. And these are all of the required functions. So if you implement these, then you can use your game inside of MCGS to solve games. Additionally, there are some optional functions such as split, and this just breaks a game into subgames. So for example, this Clobber position is equal to this sum. We could also write it this way as star and up using the basic CGT game types. And in this case, this would take advantage of the optimizations that we have for these games. Additionally, there's a normalize function to convert games to one unique representation. So for Clobber, we might remove the redundant empty spaces and flip the board. Together, these functions increase transposition table hits. Optionally, so instead of recomputing the local hash every time the state of a subgame changes, the functions which change the state can do it incrementally. These are functions like play and undo move. We have a database of endgame positions, and it stores pre-computed information about subgames. Right now, we just store the outcome classes, and this helps with some simplification and speeding up search by allowing earlier termination. Currently, we only store single subgames, which are both normalized and which don't split further into subgames. This is to keep the size of the database down. We don't store sums in the database yet. That's coming in a future version. The database is queried using local hashes. The database creation process uses this other abstract type, the database game generator. And its purpose is to generate the games that the database will create entries for. And it does it in the order that they're generated. We generate them in order of increasing size, and this ensures that the process is fast because after you play a move, the result will be in the database. So it will be quick to find its outcome class. The design of these database generators is reusable and modular, so you might not have to write code from scratch for this. Sometimes it takes like 5 minutes to add a new game to the database. We do several sum optimizations, such as for the basic game types. So for switches, which are these games here with the rationals A and B, sometimes we extract the mean or convert them to numbers. We also sum up rationals and integers. We add numbers together, and we sum multiples of up and down. We also look up subgames in the database to prune games with outcome class P. And sometimes the outcome classes can determine the search result. Additionally, after we play a move on a subgame, we use the split and normalize functions. And this increases transposition table hits. So some experiments, I'll show the diagram and then I'll talk about what's going on in the diagram. And then after that, we'll interpret the results of it. So we do scaling results for several different game types, and we generate random games, which we sort into buckets along the x-axis. So here, the different ablation settings are clustered around the buckets here. And the y-axis is the natural logarithm of the search node counts, where a search node count is just an invocation of the recursive search function. Each ablation setting uses the same set of games, and we change 3 variables between them. One is the transposition table, whether or not it's used, whether or not we split and normalize games, and whether or not the database is used. And as we go to each next option, we only add stuff. So here we have no optimizations, and then we add the transposition table, splitting and normalizing, and then the database. Any game which timed out under any of the optimization levels is excluded. So here we have linear clobber in the top left, and then here is linear no-go. Both of these games, the x-axis is the number of moves for the first player at the root. And then here is elephants and rhinos, and its x-axis is the number of stones at the start of the game. So as we can see, as we add more of these optimizations, it's an improvement of orders of magnitude. And the performance scales best when we enable the database. However, this effect diminishes along the x-axis. It's likely because we only store outcome classes now, and those become less useful as the games get really large. So these last 2 ablation settings sort of converge. I don't think I want to show that slide. Okay. So MCGS fills the gap between these combinatorial games-based packages, which rely on canonical forms, and the other solvers which use monolithic states instead of subgames. These generic optimizations of the transposition table and the database and subgame structure are useful for a variety of different game types. And there's a lot of future work that we have yet to do, such as storing sums in the database and adding more fields and more games and more move ordering heuristics. And the source code for this is also available under an MIT license. And that's it.
Thanks a lot for this wonderful talk. Again, I think it's great that you provide this all under the MIT license. Again, if there's a question from the audience, feel free to state it in the Q&A. If I understood correctly, if you want to let this solver tackle a new game, you have to touch C++ code, right? So there's no, let's say, easy language, right? To state your game and just plug it into the solver.
Yeah, you have to write C++.
Yes.
Though the interface, we try to keep it reasonably simple, so you don't have to do any weird templating nonsense for the most part.
Yeah, very good. So there's a question in the Q&A. You mentioned that the goal was to provide a general framework. Is it therefore applicable for GDL or LUDI? How much work would it be?
I'm not familiar with those. Sorry, what are those?
So as far as I know, but I guess there are better experts here on LUDI, which is a framework where you can like have a specific language on how to describe the rules of a game and plug it into into their solver framework. So, but if you're not familiar with the other frameworks, I guess it would be good if yeah, you can check those out, I think. There's another question. So is it easy to add new CGT games to your framework and use it directly to solve them? What needs to be implemented, and are there techniques you mentioned? Are these applicable to all games?
Let me go back to that slide. So to implement a new game, you just have to implement basically these functions. I don't know if that is a complete answer to the question, sorry.
Okay, so there's another sub-question in this, which was, are the techniques you mentioned applicable to all games? Or are these more game-specific techniques?
We don't support loopy games, so I guess in that sense it's not applicable to all games.
All right, okay. Any further questions? Yeah, go ahead, Duchen.
Thank you for your presentation. And I want to ask about the database. You mentioned you create a database for each game and it's requires some time to set up for the first time. So how large is the database for a game and where should it be stored?
So it's very game dependent. Some games, I don't have concrete examples for different game types, but some different game types, fewer fraction of, let's say, all 3x3 boards will split or normalize. But we store currently from 1x1 boards up to 3x3, and they get stored on disk in a file.
So,
Oh, and then for the strip games, we store up to 16. So I think in the paper we use 15.
Okay, so no special database, for example, MySQL or similar things, need to just store the files in the PC disk.
Yeah, we have our own sort of database type that does it. We don't use like a external library for it.
Okay, I see. Thank you.
Okay. So if there are no more questions, thank you again for your talk. I want to also thank all the speakers in the session, also for being perfectly on time. Then thanks for attending this first paper session.